In this installment, we're going to look a little more closely at gravity on an inclined plane. We've already dealt with the force of gravity and the force of normal on an inclined plane. We've identified this as the force normal, which by definition is perpendicular to the inclined plane. And this is the force of gravity, which points toward the center of the Earth. And that's how we draw them. How we know how to draw FGs, it should be pointing toward the center of the Earth, and normal should be perpendicular to the surface. Our objectives are to be able to draw these four on an inclined plane correctly, and use Newton's second law to explain the relative sizes of them when they draw them. So we need to get the geometries right and the magnitudes right. So in this next one, you can see I've got my force normal and I've got the force of gravity. But the motion we're looking at is going to be parallel to the inclined plane. That's what we care about. And gravity is not really in that coordinate system. What we really want to do is express gravity in terms of the geometry of the inclined plane. Now, when an object is placed on an inclined plane like this, we know that gravity is pulling it down. It's pulling it downward, but it's also pulling it inward. It's not just floating in the air. So gravity is pulling it into the plane and downward. We can draw this force of gravity vector by breaking it into its components. This component is a component of gravity, and this is a component of gravity. Down here, it's easy to see that this is the part of gravity that's parallel to the inclined plane. It's the part of gravity that's pulling it down the inclined plane. This component is perpendicular to the surface. It's normal, but underneath. So we call it the force of gravity perpendicular. So normal means perpendicular to the surface, and so does force of gravity parallel. It's just underneath. So that is how we draw these two. We draw force of gravity and its components perpendicular and parallel. Now the problem with drawing it this way, so that's the basic idea. Now let's go a little more clearly. We could draw this like so, and we can draw it this way, or we can draw it as its components. We can't draw it this way, because drawing it that way means we are drawing the force of gravity twice. We have the force of gravity here, and we have its two components. So we're actually drawing the force of gravity twice. So we either need to draw it as the force of gravity or as its components. Now, for our utility, what we care about is the forces acting on this body, shown by this little dot. So there is a part of gravity pulling it into the plane, and there's a part pulling it down the plane. Now, in terms of the size of these things, what we know is, when we use Newton's second law, is F net is the sum of the forces. And the net force is ma. And we treat one dimension at a time. So we're looking at these two. So this is the force normal, and this is the force of gravity perpendicular. So the sum of the forces are force normal and the force of gravity perpendicular. Now, if this body is sitting on the inclined plane, we would ask ourselves, is it accelerating in this direction? And the answer is no. It's sitting on this inclined plane. And even if it moves down the inclined plane, it is not. There's no acceleration in this direction, perpendicular to. So that means the acceleration is zero. And therefore, the force normal is equal and opposite to the force of gravity perpendicular. These two are equal and opposite to each other. And the only time they won't be equal to each other is if the object is breaking through the inclined plane. That's the only time they won't be. So since these two balance each other out, they add to zero, the overall net force is here. There's no acceleration in this dimension, but there is acceleration in that direction.